Hello friends, I welcome you in lecture number 6 on heat equation. In this lecture we are going to discuss another case for heat equation in which we will consider that given metal bar is having insulated ends, that is both the ends of the bar are insulated. So far we have discussed the heat equation in which we have the boundary conditions that temperature is 0 at both the endpoints. That was our first case. We must be familiar about these two types of boundary conditions. So far we have discussed those type of problems on heat equation in which we are having 0 temperature at both the endpoints of a given metal bar, and sometimes instead of this type of boundary conditions they can give us this type of boundary conditions, that is temperature gradient del U by del X is 0 at both the endpoints. So in this case we have different solution as compared to this one. So this was the first case and we have discussed enough number of problems on this first case, and we have seen that in this case the solution of heat equation satisfying these boundary conditions and initial condition given by ux0 equal to fx is given by sigma bn sin n pi x over L e raised to minus lambda n square times t. N takes the values 1 to infinity. So this was the solution for the case in which we have 0 temperature at both the ends. Now we are going to discuss another solution for the case of this type of boundary conditions, that is first order partial derivatives of u with respect to x are 0 at both the endpoints. So in this case the solution is different from this solution. So be careful whenever you are given the problem of heat equation. First you check whether you are given this type of boundary conditions or this type of boundary conditions, and we have discussed enough number of problems for the boundary conditions of this type, that is temperature is 0 at both the ends of the given metal bar. In this lecture we are going to discuss that what will be the solution for this type of boundary conditions, that is temperature gradient is 0 at both the ends, and this can be given in a descriptive form also. They can write that find out the solution of heat equation in the case that both the ends of the bar are insulated. So ends are insulated, that means no heat can flow through the ends. There is no heat flow through both the ends of the bar, and physical experiments show that a rate of heat flow is proportional to the gradient of the temperature. That means this rate of heat flow is given by partial derivative of u with respect to t, and temperature gradient, here we are considering only one space variable x, therefore temperature gradient is del u by del x. Now if no heat can flow through the ends, that means rate of heat flow is 0 or del u by del t is 0, therefore del u by del x is also 0. So if both the ends of the bar are insulated, that means temperature gradient is 0 at both the endpoints, and in that case we have to discuss that what will be the solution if both the ends of the bar are insulated. And initial condition is same, that at time t equal to 0 temperature is function of x and value of x lies between 0 and L. L is the length of the metal bar. In this lecture we are going to discuss that what is the type of solution for the metal bar with insulated ends or with this type of boundary conditions. So I will discuss that solution that I have written here, and I will explain each and every step for this case. Bar with insulated ends, that is del u by del t equal to c square times del square u by del x square, and this we have to solve with respect to the initial condition ux0 equal to fx and these two types of boundary conditions. So as usual we will apply the method of separation of variables, and for that we assume that our solution u is the product of two functions of x and t. Capital X is a function of x only, capital T is a function of t only. So we start by assuming this solution in the product form, and our equation is del u by del t equal to c square times del square u by del x square. So from this we find that del u by del x is x dash t and del square u by del x square is x double dash t. Similarly del u by del t is x as it is t dash. So we substitute these values here and we obtain this equation. Del u by del t is x t dash c square times del square u by del x square is x double dash t, and then we separate the variables and we have x double dash over x equal to t dash divided by c square t. Now x is a function of small x only, therefore this quantity is also a function of small x only. Similarly capital T is a function of small t only, therefore this is also a function of small t only, and x and t are independent variables, and we have two functions, one for function of x and another for function of t. So this equality can only be true if both the functions are equal to the same constant, say k. So that we have written here, this can only be true if each side is equal to the same constant denoted by small k, and this will give us two ordinary differential equations. If I take x with k, I will have x double dash minus k into x equal to 0, and if I consider these two, I have t dash minus c square t into k equal to 0. So that I have written here. Now we are given that this del u by del x is 0 at x equal to 0 and at x equal to L, and we have assumed that u equal to x times t. So del u by del x is x dash time t. This is at any point xy, at any point x comma t. This means x dash at point x and t at point t, and here we have to consider that del u by del x at x equal to 0 and at any point t is 0. So if I consider small x equal to 0 here and t as it is, I will have x dash times 0, x dash of 0 or x dash at point 0 and t at any point t equal to 0. So there are two possibilities, either this is 0 or this is 0, but if we take capital T equal to 0, then u becomes 0, that is trivial solution, and we are interested in the non-trivial solution. Therefore we consider x dash 0 equal to 0. Similarly, if we use this one, del u by del x is 0 at capital L, then we will have x dash at capital L and t of t equal to 0, and t of t equal to 0 gives us u equal to 0. Therefore we must have x dash L equal to 0. So here also we obtain two boundary conditions for this capital X, which says that first derivative of x is 0 at small x equal to 0 and at small x equal to L. So these are two boundary conditions, and we have to find out solution of this equation number 5 satisfying these two boundary conditions. That means we will solve that x double dash minus kx equal to 0, provided that x dash and x dash is 0 at small x equal to 0 and at small x equal to L. And now we solve that equation number 5 together with these two boundary conditions. And this k is any constant, so there are three possibilities depending on the sign of k, whether k is 0, positive and negative. So we find out the solution of 5 with 7 for each possible value of k. So first we consider that small k equal to 0, and what is equation number 5? X double dash minus kx equal to 0. X double dash minus kx equal to 0. This is number 5. If I take k equal to 0, I will have x double dash equal to 0, and therefore solution is capital X equal to a into x plus b. Okay, this we can easily obtain. X double dash is function of x only. So if I integrate this with respect to x, I will have x dash equal to some constant, say capital A. And if I again integrate with respect to x on both sides, I will have a into x plus b. Or I can write down the auxiliary equation corresponding to this, that is m square equal to 0. Therefore I will have m equal to 0 comma 0. Therefore x equal to a into e raised to 0x plus b into e raised to 0x. But these two are same, so we multiply one function by small x, and e raised to 0x is 1. Therefore x equal to ax plus b. Now we have to find out particular solution of 5 satisfying these two conditions. So conditions are, first derivative of x is 0 at both the endpoints. So we obtain, first we find that derivative of this x is capital A, and we have x dash 0 equal to 0. So if we use this condition, then we can see this is capital A at any point x. So x dash 0 equal to 0 will give us a equal to 0. Okay, if I take x equal to 0 here, left hand side is x dash at any point. So x dash 0 is given to be 0. Okay, if we take x equal to 0 in this equation, we can write in this way, x dash 0 equal to a. But x dash 0 is given to be 0, therefore capital A equal to 0. And if I take capital A equal to 0, here I will have capital X equal to b. Now second condition is x dash at L equal to 0. But we can see this is 0 at every point, every value of x. So this condition is satisfied for any constant b. So this I have written here, x dash equal to 0 for any value of b. So therefore our solution is capital X equal to b. Here we put a equal to 0. So solution of 5 satisfying conditions given by 7, that is x dash 0 equal to 0 equal to x dash L, is capital X equal to b. In short, we obtain the constant value for the solution of equation 5, that capital X is equal to some constant, arbitrary constant, say b, and it satisfies both the conditions. If we wish, we can consider particular value of b. We can take b equal to 1, then we will have x equal to 1. That is the solution of 5. And we have another equation also that we can solve by taking k equal to 0. Suppose I take k equal to 0 in equation number 6, then I will have t dash equal to 0, and if I integrate both sides with respect to t, I will have t equal to some constant, say capital D. So now our equation is u equal to x into t, and here we have obtained that capital X is constant, and we obtained that capital T is also constant. That means our solution in this case is going to be u equal to x is constant, t is also constant, that is u becomes constant. And if we use initial condition is at t equal to 0, value of u is fx. Suppose I put t equal to 0 here u is constant for any value of x and t. So here we can see that for t equal to 0 also we have constant, and that is given to be fx. So initial condition is satisfied if fx is constant, and in this case the solution is u equal to some constant. So here we can write that u x t equal to x into t. X we have obtained, that is capital B, and t also we can write, t is going to be constant, and we know that this solution satisfies initial condition if fx is constant, and in this case the solution is u equal to constant. So there is some contribution for this case also, k equal to 0. In earlier lectures we had seen that k equal to 0 was giving us the trivial solution, but here we get non-trivial solution which is constant. Now second case is, suppose k is positive. So if k is positive, then we can assume that k is square of some real number which is non-zero. Suppose k equal to mu square. Now equation number 5 is x double dash minus k x equal to 0. If I take k equal to mu square here, I will obtain this equation, and its general solution is given by this. Okay, now we are familiar with this. We can solve this by writing its auxiliary equation, which is m square minus mu square equal to 0. This will give me m square equal to mu square, and hence m equal to plus or minus mu. Therefore the general solution is x equal to a times e raised to mu x plus b times e raised to mu x. This a and b are arbitrary constants, and we have to decide these values of a and b using these two conditions, that x dash is 0 at 0, x dash is 0 at x equal to capital L also. So for that we differentiate this with respect to x. Derivative of e raised to mu x is e raised to mu x into derivative of mu x is mu. Same thing here, e raised to mu minus mu x has derivative itself, and into derivative of minus mu x with respect to x is minus mu. So we are applying chain rule here, and then we can directly use the condition. Suppose I use this condition, x dash 0 equal to 0. That means I will put small x equal to 0 and x dash equal to 0. So from this I will obtain 0 equal to a into mu e raised to 0 minus b into mu e raised to 0, that is 1. So I obtain a into mu minus b into mu equal to 0, and because mu is non-zero we obtain this equation, a minus b equal to 0. Similarly we put x dash equal to 0 when small x equal to L. So we use this condition. This means when small x equal to L, x dash is 0. So here I put x dash equal to 0, and here I have to write capital X small x equal to capital L. Same thing here, e raised to minus mu into L. Here also we can cancel out this mu, and we are having this equation, a into e raised to mu L minus b into e raised to minus mu L. And if we solve this equation number 8 and 9, we will find that a and b both are 0. Okay, this is easy to solve. You can multiply this equation 8 by e raised to mu L. Suppose I consider multiplication of this by e raised to mu L, I will have this equation, and if I subtract this equation from equation number 9, you can see this is going to be 0, and I will have b into e raised to mu l minus b into e raised to minus mu l, and we can take b common equal to 0, and this can never be 0, so b must be 0, and a and b are equal, therefore a equal to b equal to 0, and then we substitute values of a and b in this equation, and we obtain that capital X becomes 0 for all x, that is capital X is identically 0, and if x is identically 0, u is the product of t with x, therefore u also 0 for all values of x and t, and we are not interested in this type of solution. This is trivial solution, therefore we reject this case that k is greater than 0. In first case we are considering k equal to 0 because in this case we obtain non-trivial solution, but that solution is u equal to constant, but we have to be careful that here we obtain non-trivial solution. And last case is k is negative. If k is negative, we can consider k equal to negative of square of some non-zero real number, that is p is non-zero, and now we again put k equal to minus p square here, and we obtain that x double dash plus p square x equal to 0, and auxiliary equation here will be m square plus p square equal to 0, and if I simplify, I will have value of m is complex plus or minus I into p, and therefore the general solution is capital X equal to a cos px plus b sin px, and we have to obtain the solution which satisfies these two boundary conditions. X dash is 0 at x equal to 0 and at x equal to L. So I differentiate this with respect to x. Derivative of cos is minus sin, and into derivative of px is p. Same thing here, derivative of sin is cos, into derivative of px is p. Now if I use this condition, x dash 0 equal to 0, that means I have to put x dash equal to 0 and small x equal to 0. So this is 0 for x equal to 0, and here I will have b into p equal to 0, but p is non-zero, therefore we obtain b equal to 0. So if we put b equal to 0 here, our x becomes a into cos px. To use second condition, I have to write x dash, so that I have written x dash here, so I can use that condition here. Now I am using that x dash is 0 at small x equal to L. So here I take x dash equal to 0, on this side I will take small x equal to capital L, but here we have b is already 0, so here we write minus a into p into sine of p into L equal to 0, b is already 0. Now p is non-zero and we are interested in the value of a. So from this we have either a equal to 0 or sin pl equal to 0, but if we take a equal to 0, then b is already 0, so in that case this will become 0, capital X will become 0, so we will consider sin pl equal to 0, so that I have written here. And if sin pl equal to 0, then we must have pl equal to integer multiple of pi, therefore p equal to n pi divided by L. So that we have written here. N is any integer, but to consider independent functions we are considering positive integers only. And here our solution is x equal to a cos px plus b sin px. B is 0, and therefore we have x equal to a cos px and p is n pi over L. Therefore we write that capital X equal to cos n pi x over L. Actually capital X is a into cos px, and we are considering capital A equal to 1. It is arbitrary constant, so we can take any value for arbitrary constant. Suppose we consider A equal to 1 and P is n pi over L. So these are the linearly independent functions which are solutions of the equation x double dash minus kx equal to 0, which satisfies the boundary conditions x dash 0 equal to 0 and x dash L equal to 0. Now we have to consider the solution of equation number 6 with this value of k. For k negative, we obtain non-zero solutions for x. So now we solve this equation for the same value of k. We solve equation number 6, t dash minus k c square t equal to 0 for that value of k, which we have taken as k equal to minus p square. So that will be t dash plus p square c square t equal to 0. So now we find out that for this value of k, now we solve equation 6 with k equal to minus of p square. And what is p? P is n pi over L, that is minus of square of n pi over L. And our equation was t dash minus c square kt equal to 0. If I take this k equal to p square minus p square, I will get k t dash plus c square p square t equal to 0. Now p is n pi over L, so here we can see that is going to be c n pi over L whole square, and we denote this quantity c n pi over L by lambda n, so that we have written here. For conveniency we consider c n pi over L by lambda n. So lambda n is the notation for this, and it is known as eigenvalue. And this is easy to solve. We separate the variables. First we write this as t dash equal to minus lambda n square t, and we transfer this t on left hand side, and then we integrate both sides with respect to small t. So here we will have this type of thing, and we can see that derivative of denominator is in the numerator. Therefore this integral is logarithm of denominator, which is t. This is constant and we are integrating with respect to t. Therefore it is minus lambda n square times t plus some constant of integration that we adjust as ln a suffix n, where an is arbitrary constant. Here we are writing constant as a suffix n because for different values of n we will obtain different infinite number of solutions, and for each solution this constant can be different, so that is denoted by a suffix n. And if we transfer this on this side and using the property of logarithm, we have log t minus log an equal to log of t divided by an. And we know that exponential and logarithmic function are inverses of each other. Therefore from this we obtain t over an equal to exponential of this. Okay, we can write one more step. From this we have t over an equal to e raised to minus lambda n square t, and in the next step we find t equal to an times e raised to minus lambda n square times t, and these solutions depend on values of n. So instead of writing t, we denote solution for each value of n by t suffix n. And finally we write down the solutions of heat equation by taking product of solutions obtained for x and obtained for t. So now we have written value of xn that we obtained as an cos n pi x over L, tn we have obtained as e raised to minus lambda n square t, and n is from 1 to 3 and so on. So we obtain these linearly independent solutions corresponding to the third case, that is k is negative. For k equal to 0, we find that solution is constant. So we denote that solution by u suffix 0. This starts from n equal to 1, 2 and so on. So we have seen that in first case, that is k equal to 0, solution was u0 equal to constant, and these are the solutions for n equal to 1, 2, 3 and so on corresponding to this value of k. K is negative. So now we know that because heat equation is linear and homogeneous, if we have these solutions of heat equation, then we can take their sum, and resulting solution is also a solution of heat equation. So now we have taken the superposition of all these solutions. So here n starts from 1, 2, 3 and so on, but to include this we will consider n starting from 0, and we will combine this with these solutions. So here I have written that by superposition principle uxt equal to sigma unxt, n is starting from 0 up to infinity, an cos n pi x by L e raised to minus lambda n square t. For n equal to 0, we can see if I take n equal to 0, this is a0, this is going to be 0, so I have cos 0 which is 1, and here also e raised to minus lambda n square t, and n is 0 and lambda 0 is 0 in that case. So for n equal to 0, lambda 0 is 0, therefore this is also e raised to 0 1, cos 0 is 1. So all we will obtain corresponding to n equal to 0 is constant a0, and that matches with this, that when k equal to 0, u0 is constant. So that solution is also included in using this superposition principle. So by superposition principle, if we know that u0, u1, u2 and so on are solutions of heat equation, then their sum u0 plus u1 plus u2 is also a solution, and therefore we can write that this 14 is also a solution of given problem. Now so far we have not used that initial condition. We had used initial condition for the case that k equal to 0, but for k less than 0 we have not used initial condition. So now we can use initial condition also. We have to decide the solution which satisfies boundary conditions as well as initial conditions. So to use initial condition, we will take t equal to 0 and u equal to fx in this equation number 14. I will write t equal to 0 and u equal to fx everywhere in equation number 14. So left hand side is u, so that will be replaced by fx, and here we have to consider t equal to 0. So t is in this term only. So what we will have, sigma an cos n pi x over L equal to fx, or fx equal to sigma an cos n pi x over L, using this initial condition which says that at time t equal to 0 temperature has value fx. But we know that this is very famous series. It is Fourier cosine series for this function f, and if we have Fourier cosine series, we know the formula for these coefficients. This we can rewrite as a0 plus sigma an cos n pi x by L n equal to 1 to infinity. And we know that a0 is given by this formula, 1 by L integral from 0 to L fx dx, and this an is given by 2 by L integral 0 to L fx cos n pi x over L, and takes the values 1, 2, 3 and so on. So this we have to remember, that the solution of heat equation for the problem that both the ends of the bar are insulated is given by this equation number 14, that is u equal to sigma an cos n pi x over L e raised to minus lambda n square t, where this a0 and an are given by this formula. So you can understand the difference. In the first case, we had considered the boundary conditions that temperature is 0 at both the ends of the bar, and in that case the solution was containing sign terms, and here boundary conditions are different, that is del u by del x is 0 at x equal to 0 and at x equal to L, and we can see the difference. Instead of sine terms, here we have cosine terms, and this a0 and an are given by these formulas. So that is the difference for both the terms. So be careful. What we have discussed now is the solution of heat equation del u by del t equal to c square times del square u by del x square, satisfying the boundary conditions del u by del x is 0 at x equal to 0, del u by del x is 0 at x equal to L. This means we have metal bar or metal rod with both the ends insulated, metal bar with insulated ends, and initial condition is ux0 equal to fx. So what we have seen, that the solution of this heat equation is given by uxt equal to sigma n equal to 0 to infinity an cosine of n pi x over L e raised to minus lambda n square t. The difference is of these terms. Cosine, this is Fourier cosine, this is matching with Fourier cosine series when t equal to 0. Here n starts from 0, and a0 is given by 1 divided by L integral of function fx with respect to x, and an is given by 2 divided by L integral from 0 to L fx times cosine of n pi x over L integral with respect to x, n starts from 1, 2, 3 and so on. So we will remember this result, that solution of heat equation together with these two boundary conditions and this initial condition is given by this formula, where this lambda n is as usual c n pi over L, n equal to 0, 1, 2, 3 and so on. For n equal to 0, we will have lambda 0 equal to 0, and this eigenvalue corresponds to the solution, that u equal to constant. So this is the difference, and we must be clear that which type of boundary conditions are given. Sometimes directly writing the boundary conditions in this form, they can just mention in the question that consider the bar with both the ends insulated with this initial condition and solve the heat equation. So you must be clear about this, that if it is specified that both the ends of the bar are insulated, then we will have to consider these initial conditions, that is partial derivative of u with respect to x is 0 at both the ends, that means at x equal to 0 and at x equal to L. So this is all about this session. In upcoming lectures we will discuss the problems based on this second case of insulated ends. Thanks for watching.